Hello my dear student friends, welcome you all to the video lecture series on network analysis. Okay, in previous lecture we have started our discussion on the new chapter that is nothing but resonance. Okay, so what is resonance and how it occurs, what is the basic fundamental behind it and all these things that we have studied. Okay, so remember that in case of resonance we are going to use only three components, right? So for resonance we are going to use R, L and C. These are the three passive components which are going to give you a resonance. Okay, so remember that. Okay, so resonance is nothing but simply matching of the frequency, matching the frequency of two different objects, isn't it? Okay, we have studied, we have seen it. Okay, fine. So you had that experiment in 11th or 12th, right? So the hollow tube is inserted into this, let us say a liquid is there, right? And you are going to move this hollow tube, right? You are going to move this hollow tube up and down, right? And in front of that you are going to put the tuning fork. Okay, so vibrating tuning fork, you are going to put it in front of this hollow tube and you are going to move this uh, tube up and down, and at certain position the very loud sound is going to occur. Okay, so loud sound is going to occur, and that is nothing but indication of resonance. Okay, so it indicates resonance, right? So this is nothing but your tuning fork. Okay, so it is going to vibrate with certain frequency which is mentioned on it, right? So it is going to vibrate it, right? And that tuning fork you are going to put it in front of that your tube, hollow tube, which has been inserted into the liquid. And whenever you are going to move that tube up and down, and at certain position is going to occur, in that case you will be getting a loud sound. Okay, so it is going to generate the large sound, and that is nothing but indication of a resonance, right? So simply this is nothing but, let us say this tuning fork is having a frequency of 100 hertz. Okay, then whenever the sound is going to generated, in that case we can say that this area is going to generate a 100 hertz frequency, or it can have resonance at 100 hertz frequency. Okay, fine. So we had to talk about what is the resistor. Resistor is a device which is going to oppose the flow of resistance, right? We had a discussion about inductor. Inductor is a coil. Inductor is a coil. Okay, simply it is denoted with this kind of symbol, right? Okay, so whenever there is a wire, if you are going to roll it like this, then it is going to create a inductor. That's it. That is very simple. Inductor actually we can call. Okay, so this is nothing but air core inductor, you can call this. Okay, so properties of inductors are nothing but what? It creates a magnetic field, or it stores energy in the form of magnetic field. Across it creates magnetic field across it. Okay, and the property is what? Voltage leads the applied current. Voltage leads the current, or in other word, current lags behind. Current lags behind the applied voltage. Because inductor it doesn't allow variable current flowing through it, or inductor doesn't allow variations present into the current. So that, remember that you might have used this inductor as a low pass filter. Okay, so whenever you are going to use this inductor in case of series, then it will be acting as a low pass filter. Okay, Is that fine? Right. So this is nothing but a low pass filter. So it will have a minimum vibrations. Okay, it will pass a DC current more without providing any kind of much resistance. But whenever the variable current is going to flow through it, or variations into the current is going to occur over there, it is going to provide some kind of opposition to that. Okay, so that is the meaning of this. Voltage leads the current and current lags behind the applied voltage. That is the meaning of this. Okay, fine. Now let us discuss what is capacitor. Okay, also we sorry, I forgot to mention XL. So XL we need to discuss. Okay, so XL is nothing but it is an imaginary resistance, or rather we are calling this as a impedance offered by the inductor, and that is nothing but omega L, right? So XL is nothing but omega L, and remember that this is nothing but an imaginary resistor. This is not the physical resistor as like that we have like a physical resistor, isn't it? So this is not a real resistance, so that's why it is called as a imaginary resistance, and that's why this J term is applied over here. Is that fine? Okay, so remember that omega is nothing but 2 pi FL, right? Omega is nothing but 2 pi F, and if I'm going to say that in a broader case, XL is directly proportional to the frequency provided that L is constant, or L is constant. Okay, so if inductor is constant, in that case the XL value is directly proportional to the frequency of signal. Okay, so let us say we have applied a AC signal, okay, having a frequency of, let us say, 100 Hertz, right? And let us say L is of 1 Henry. Okay, so XL is nothing but 2 pi into 100 into 1. Okay, so it is nothing but 200 pi is the value of XL. That means XL is nothing but 200 into 3.14. So that will be the value of XL. Is that fine? So it may be a 600 something around, right? Okay, so that will be the value of XL, and this is nothing but a resistance, imaginary resistance offered by the inductor. Remember that while discussing about your mesh analysis, we had J6 minus J6 ohms. Okay, so this was for XL, that is nothing but the inductor, and this we used for XC, right? Okay, so while discussing your AC analysis of mesh analysis, in that case we had this kind of resistances, and those are nothing but represented for the inductor and capacitor. Remember that. Okay, great. Now let us discuss capacitor. Okay, so capacitor, what is capacitor? Capacitor is simply a device, okay, it is a component which stores energy in the form of electric field. In the form of electric field. What do you mean by electric field? Now remember that capacitor is nothing but consisting of only two parallel plates of conductor, okay, and they are separated with some insulating material. So it is nothing but a insulating material. Okay, so insulator. So whenever we are applying supply to, let us say, capacitor, what is going to happen? Let us say this is my battery. Okay, so let us say I have connected a plus 5 volt battery over here, and let us say this is my capacitor. Okay, so slowly the charges are going to get accumulated. Okay, so current is going to flow because of flow of electrons or ions. Okay, so current is going to flow, and then the voltage or the polarities are going to get accumulated, or charges are going to get accumulated across the plates, because there is no path to travel from this plate to this plate. Okay, so they cannot travel it. Okay, because the insulating material is present in between these two plates. So as the insulating material is there, so definitely these ions cannot transfer from one end to another end, and that's why the problem is what? They cannot transfer the ions. But what is going to happen? The plates are going to have the accumulation of the charges. Okay. So at this point, the positive ions are going to get accumulated, and at this place, the negative ions, that is nothing but my electrons, are going to get accumulated. And whenever this accumulation is going to occur, it is going to create one voltage. Okay, so remember that voltage is nothing but the differences of the accumulation of the charges, that is nothing but potential difference. Okay, so remember that whenever we are going to apply supply to the capacitor, it starts charging. So it starts charging, right? So as like our mobile batteries, so mobile batteries are, we can say that up to some extent these are nothing but my capacitors. Okay, so remember that our mobile batteries are nothing but also a type of capacitors. Is that fine? So remember that whenever we are going to apply a supply, so gradually it is going to accumulate all the charges. So charges are going to get accumulated across the plates, right? And once the charges are going to get accumulated, the voltage across these two plates is going to have some value. Okay, and this is nothing but a collective effect of all the positive and all the negative ions, and that is called as a potential difference. Remember that. And once the battery is fully charged, then it cannot go for higher charging. Okay, so that's why once the maximum level of the accumulation of the charges is going to occur at that place, then no amount of more charges can be accumulated over there, because the capacity has been now fully executed. Okay, so that's why there are no extra places to accumulate the charges. So that's why we used to say that now my battery is charged 100%. Okay, like that. So remember that capacitor is a component which is going to store. Yes, it is storing the energy, and this energy is in the form of electric field. Are you getting it? So this is nothing but an electric field, isn't it? So remember that the capacitor is a component which stores energy in the form of electric field. Okay. Now, as the current is going to first flow, and then the voltage is going to accumulated or generated or stored, or voltage is going to get generated across the capacitor. So here the property of capacitor is what? Current leads. Okay, so here current leads the applied voltage, and then the applied voltage is going to get created across that two terminals of the capacitor. Okay, so current leads the applied voltage. Okay, so remember that here voltage lags behind. Voltage lags behind the current. Okay, so either of in both the ways you are going to write it, but the meaning is one and same. Okay, so remember that this is nothing but property of a capacitor. Is that fine? Okay, now let us discuss resonance. Okay, so how we are going to generate the resonance by using these two components. So remember that resonance is going to occur, resonance will be present if the current flowing through the circuit is in phase with the applied signal. Then the resonance will generate. Okay, so we can say that the resonance is going to occur if the current flowing through the circuit, let us say, if it is in phase with the applied signal, then and then only we can say that the resonance is going to occur. And whenever the resonance is occurring, the current is maximum. Okay, at resonance maximum current flows. Okay, now let us discuss the types of resonant circuit. Okay, so there are three types. One is series resonance, series RLC resonance. Then parallel resonance circuit, and third one is tank circuit. We will discuss it. Okay, so remember that we are going to use only three components. Okay, we are going to use only three components. Those are nothing but R, L and C. And remember that L is having lagging property, right? Current lags behind the applied voltage, and capacitor is having leading property. Okay, so as we are using these three component, and resistor is not again it does not have any kind of leading and lagging property. Okay, so we can say that neutral in case of phase shift. Okay, so who is going to provide the phase shift? Only these two components are going to provide phase shift or change in the phase angle. Okay, so these are the two components which has the property of leading and lagging. So therefore, because of that, there may be a chances of becoming out of phase. The current is going to get out of phase with the applied supply. Okay, and because of that, it may not create the resonance. So ultimately, what is the main fundamental of the resonance? We need to create if we want to create the resonance, then what is the condition? The current which is flowing through that particular RLC circuit, that must be in phase with the applied signal. Okay, but as we are using inductor and capacitor, then they are going to provide some kind of leading and lagging facility, right? So if we are going to tune in such a way that the leading and lagging angles are going to become same. Okay, so if the angles are becoming same but the angles are leading, one is leading and another one is lagging, so plus and minus is there. So if I am going to add it together having the same magnitude but the polarities are different, then we can create the zero, right? That means the phase shift is going to become zero. That means let us say if this inductor is providing a lagging current, let us say a 90 degree. Okay, plus 90 means let us say I have applied voltage at this point. Okay, and my current start increasing after this. So is it lagging? Yes, I have applied voltage at this point, right? So at t is equals to 0 I have applied current, but at let us say 3 seconds it start increasing the amount of current. Okay, so this is called as lagging. Okay, and this is nothing but a plus. So 0 plus 3 seconds is nothing but the lagging time. Okay, so current has lag behind this applied signal. Okay, so that's why it is mainly termed as plus sign. Okay, so plus 90 for example. Okay, or in more broad way, let me show you. Suppose I have applied AC sine wave. Okay, and let us say this is nothing but my 90 angle, and from this point the current started increasing. Okay, so this is nothing but applied voltage and this is nothing but the resulted current. Got it? So is it a delayed signal? Yes, definitely. So it has lag behind, no? Voltage we have applied first, but after few time the current started increasing, right? So this is nothing but a lagging property. Okay, but that is in a reverse case in case of capacitor. Okay, So current is going to lead than the applied voltage. Okay, so suppose I have a capacitor, okay, and if I'm going to check the voltage drop across the capacitor, then first current is going to increase, right, and then the voltage across it is going to increase. Got it? So this is nothing but the current flown through the circuit, okay, and this is nothing but the voltage which will be created across that capacitor. So remember that in this case the current is in advanced position, that means a minus 90 degree. Okay, so 0 is over here, and let us say this is nothing but a degree. Okay, so it has started initially and then voltage started increasing in proportion way after some time. So remember that here the current is leading, so that's why it is represented with minus, because it is before 0. So whenever the value comes before 0, we used to write it as minus, right? So that's why that my 90 is having minus sign. Got it? Okay, I hope the fundamentals of your inductor and capacitor is clear. And if I want to have the current in phase, let us say I have a circuit in such a way that it is having these three components, right, and a supply, AC supply has been applied to it. Okay, if I want to have the resonance, what is the condition? The condition is that this phase angle must be 0. Okay, so overall effect of this phase angle must be 0 for the current. That means the current must be in phase with the applied signal. Okay, so if the current is going to become in phase with the applied signal, that means if the XL and XCs, right, remember that if XL, value of XL and value of XC, if it is same, then and then only the amount of phase angle, that is leading and lagging, is going to become same, and the resultant of the phase angle is going to become 0. Okay, so that is the condition of resonance. Remember this one. Okay, so this is nothing but the condition of resonance. Okay, fine. So let us discuss the in detail RLC circuit. I hope this circuit you understood properly. So we'll discuss first type of circuit, that is series resonance, series RLC circuit. Okay, so first type of circuit is series RLC circuit. Got it? Okay, so let us draw the series RLC circuit. Series means we have a series connection of these three components. That's it. R, L and C are connected in series. That's it. Okay. So the name itself indicates what exactly the type of circuit is. So let us draw R, let us then draw L, and let us draw C. That's it. So this is nothing but my series RLC circuit. Okay. And remember that this is nothing but the supply. Let us say I have a FM circuit, right, and FM transmitter is there and FM receiver is there. Okay, and we used to take the signal, FM signal, through which antenna, definitely. So whenever we are having, let us say, FM receiver, we used to have an antenna. It may be a single wire as well. Okay, no doubt. So let us say we are feeding the FM signal, okay, FM signal to this circuit, right? So this is my RLC circuit, which is going to have, or which is going to tune to this particular, let us say, FM signal. Okay, so remember that the antenna wire is connected, let us say, over here, and the ground signal is been connected over here. So this is nothing but simply my series RLC resonance circuit. Let us say this is having a 98.3 megahertz signal, right, and we have fed that signal to this, let us say, series RLC circuit. Okay, we'll discuss that, how to generate, how to calculate, and all these things, all the values of components and all these things, that we will discuss laterwards. But remember that right now we have fed what? We have fed the signal, FM signal, to my resonant circuit. Okay, remember that over here we are not applying any kind of function generator and all these things. Okay, we can directly apply the signal which has to uh, which whose frequency has to be matched with this particular resonating circuit, or we need to generate the resonance of, let us say, this particular kind of frequency. Okay, so either we can change this one or this one. So if we are going to mention this as a capacitor, so this is nothing but termed as a variable capacitor. Okay, whenever this is nothing but an inductor is there and arrow is there, then it indicates that variable inductor. Got it? So either one of this has to be variable. Okay, so remember that not both, but out of these two, either inductor or capacitor must be variable. Okay, fine. So that is the condition. Okay, now if I want to write the impedance for this particular circuit, how I can write it? So remember that JXL is nothing but the inductor resistance offered by the inductor, and minus JXC is nothing but the resistance offered by the capacitor. That's it. If I want to generate total impedance provided by this circuit, how I can write it then? A resistor, all the components are connected in a series, that's why R plus JXL minus JXC, isn't it? Yes, definitely. So impedance of the circuit is nothing but can be written like this: R plus J into, we have taken J common, that's it. Okay, and if I want to find out the magnitude of inductance, so is it forming a plus JB form? Yes. So if I want to have real time or real part of this particular A plus JB form, how I can convert it? I can convert it by simply taking A square plus B square, isn't it? So this is nothing but my impedance, real time impedance or real part of that particular impedance. Got it? So what is XL? XL is nothing but, sorry, not a multiplication, it's a addition, right? So XL is 2 pi FL. What is XC? 1 upon 2 pi FC, right? Yes, so this is nothing but my real part of impedance. Okay, I hope you understood this. What is the condition of resonance? When the resonance is going to occur? Whenever the phase angle of inductor and capacitor is going to have same but opposite values. Okay, equal and opposite values, then and then only their phase angles are going to get neutralized, and because of that the current which is flowing through this particular circuit is going to become in phase with that particular applied signal, and then we are going to say that the resonance is occurred, or we have matched the frequency of applied signal and the series RLC circuit. That's it. Okay, so remember that we have the condition at resonance. Okay, so condition of resonance is what? XL must be equals to XC. Okay, what is XL? XL is nothing but 2 pi FL. What is XC? XC is nothing but 2 pi FC. Right? Now can you find out the frequency of resonance then? Yes, definitely. Let us take this term to the left hand side. So 2 pi FL multiplied with 2 pi FC is equals to 1. Right? Now let us do the multiplication, and what is going to happen? This is nothing but 4 pi square F square, sorry, 4 pi square F square LC. So can I write FR? It is nothing but the frequency at resonance, no? So we have defined this as nothing but the condition at, it is the condition of resonance, no? So can I write it as suffix as R? So frequency is nothing but the frequency of resonance. Yes, definitely. So that's why I have used resonance suffix R. Okay. So from this, can I find out Fr square is equals to 1 upon 4 pi square LC, right? And let us take now square root, taking square root. Taking square root on both sides. Okay, so therefore Fr is equals to what? 1 upon 4 pi square is nothing but 4 square root is 2, pi square root is pi, and then under root LC. Okay, so this is nothing but the frequency formula to calculate the frequency of resonance. Okay, fine. So let us check it out. Let us take some few example based on this. Okay, so example number 1. Calculate the frequency of resonance if the circuit consists of R is equals to 10 ohm, L is equals to, let me take one example whatever I have taken in my class. Okay, so 0.5 Henry, millihenry, not Henry, and C is equals to 10 microfarad. Okay, also find impedance at resonance. Okay, fine. So how to find out? Okay, so let us take the write the answer given. First we need to write the given terms. Okay, R is given, that is 10 ohm, L is given 0.5 Henry, 0.5 millihenry, and C is given 10 microfarad. Okay, and what you are going to find out? They are asked to find out resonant frequency and impedance at what? Resonant frequency at Fr. Okay, so impedance at resonance you need to find out. Okay, fine. So we know the formula for resonant frequency. Fr square is equals to 1 upon 4 pi square LC, right? So put the value of L and C over here. So 1 upon 4 pi square. What is L? L is nothing but 0.5 milli. Milli is nothing but 10 raised to minus 3. Okay, so let me write it over here. You know very well what is milli. Milli is 10 raised to minus 3 and micro is 10 raised to minus 6. Right? Okay, into 10 into 10 raised to minus 6. So if you are going to calculate this one, what will be the answer for this? It will give you the resonant frequency. Let me calculate directly Fr. I will compute this value and I will take the square root of it. So it is nothing but giving me value as 2.250 kilohertz. So it is giving you 2.250 kilohertz. Okay, so this is nothing but the frequency of resonance. Okay, now they have been asked to find out Z at FR. How to find it out? So formula for Z is nothing but what? Z is equals to R plus JXL minus XC. This is the condition. But at resonance, XL is equals to XC. Yes, at resonance, this is the condition, no? Since the condition is. Okay, so therefore, what is the value of R then? What is the value of Z? Z will be, let us say, I am going to put XL is equals to XC. So it is going to become XC minus XC is going to become 0, right? So J XC minus XC, it is going to become 0. So therefore, value at Z is nothing but R and value of R is nothing but 10. That's it. So simple. So such kind of problem may be asked in your examination. Is that fine? I hope you understood. Okay? Is that fine? Great. So we'll conclude over here and we'll continue in the next lecture. Okay, now let us take one more example based on the resonance. Okay, so let us take one more example. Suppose if the resonant frequency is given to you people and one of the component is not given, then you need to find out the component. Okay, so find the value of capacitor, find the value of capacitor so that the circuit will resonate at 1 kilohertz, let us say. Okay, the circuit components are R is equals to, again let us say 10 ohm and L is equals to, let us say, okay, R is 100 ohm not 10 ohm and L is nothing but 0.1 millihenry. Okay, millihenry. Is that fine? So first we need to write what are the given terms. So what are the given terms? They have given FR is nothing but 1 kilohertz, right? They have given R is equals to 100 ohm and L they have mentioned as 0.1 millihenry. What they have asked? They have asked the value of capacitor. Okay, you need to find out the value of capacitor. Okay, fine. So formula is what? FR is equals to, so I am directly writing as FR square is equals to 1 upon 4 pi square LC, right? And I need to find out this one. Okay, so let me take this term to the left hand side. So C is equals to 1 upon 4 pi square F square, that is FR square L. So by means of this formula I can find out the value. Okay, so 4 pi square into 1000, 1 k is 1000 square into 0.1 millihenry. So how much is the value of capacitor? It is giving you value as 10.13 microfarad. So 10.13 microfarad is the value of capacitor. So likewise you can find out the value of capacitor. Okay, on the similar note, let us take one more example in which you need to find out the inductor. Find the value of inductor, that is L, so that the circuit will resonate at 1 kilohertz. Having the circuit components are just a minute. Okay, sorry. In the previous in this particular example, FR is 5K. Sorry, FR is 5 kilohertz. Okay, so over here the value of resonant frequency is not 1 kilohertz, it is 5 kilohertz. Sorry, I have taken instead of 1 kilohertz, instead of 5 kilohertz I have taken 1 kilohertz. That is not the case. Okay, fine. So you can calculate the value of that particular capacitor for 1 kilohertz frequency, no problem. But the thing is that you are going to put the value of FR over here, ln of FR you are going to put it in this equation and you are going to get the value of capacitor. Okay, fine. So over here as well, this is not 1 kilohertz. The value of frequency is 2 kilohertz and the circuit components are R is equals to 100 ohm and C is equals to 4.7 microfarads. Okay, so let us find out the inductor value. So what are the given terms? FR is given, FR is 2 kilohertz, resistor value is given as 100 ohm and capacitor value they have mentioned as 4.7 microfarad. Okay, what they have asked to find out? They have asked to find out the value of inductor so that it will generate the resonance of, or this circuit will generate the resonance of 2 kilohertz. Okay, so let us find out again. FR square is equals to 1 upon 4 pi square LC. So L you are going to find out, so therefore 1 upon 4 pi square FR square C. Okay, so once I am going to put the values of FR and C, I will be getting the value of L as 1.14 millihenry. Okay, so it is going to give me 1.14 millihenry. So likewise you can find out the value of resonant frequency, the value of capacitor and the value of inductor. Okay, fine. Now let's go for the next point. Now we are going to discuss sketches of curves of inductor, capacitor and resistor for series as a function of frequency for a series RLC circuit. Okay, so let us discuss the curve. Fine. Now tell me, okay, what is impedance? Impedance is nothing but under root of R square plus omega L minus 1 upon omega C, it's a bracket square. This is the impedance curve, right? Sorry, impedance equation. So tell me what is XL? XL is omega L. So XL is directly proportional to the frequency. Yes. What about XC? XC is inversely proportional to the frequency, isn't it? So let us say if this is my impedance Okay, say now my frequency is right now starting from 0. Okay, what is the value of xc then? Xc is infinite. 1 upon 0 is definitely infinite, right? So 1 upon 0 is equals to infinity. So for DC signal, the capacitor is acting as an open circuit. Remember this one. Okay, as it is indicating the high impedance, that means there is there is a large amount of resistance, that is infinite resistance, and there is no connection in between the 2 points. Okay, so that means the impedance of this particular capacitor is infinite, and as we are increasing the frequency, if the frequency is increasing, what is going to happen? Xc is going to decrease. Yes. So as the frequency goes on increasing, the value of capacitor is going to give some finite value, okay, which is less than infinite, right? But on the similar note, what will be the value of XL for 0 frequency? It will be 0, right? And as F is going to increase, what is going to happen? XL is also going to increase because it has a direct proportion, right? So it is directly proportional to the change in the frequency. So remember that whenever the XL is going to increase, right, if the frequency is going to increase, XL is going to increase. But in case of capacitor, if frequency is increasing, then XC is going to decrease, right? If the frequency is decreasing, XC will definitely increase because they have inverse relation. Okay, and finally this is nothing but my total impedance of the particular circuit. Okay, at resonance, this Z is nothing but R, right? So let us draw that curve. Okay, so let us say this is my curve. Okay, let us say this is XC. Okay, then value of resistor will be constant, isn't it? Value of resistance, let us say if it is 100, it will be continuously remain 100, or it will change? No, it will not change, right? Okay, so remember that. Sorry, just a moment, something is missing. Okay, so let us say this is R, and the XC is going to decrease from infinite, it will touch at resonance, and again it may increase. Okay, is that fine? Sorry, it is Z, not sorry, it is Z. Okay, let me redraw it, let me explain it properly. XC is negative, right? Minus J XC we used to write. So at lower frequencies, the value of capacitor is very high, and as the frequency goes on increasing, it will give you some finite amount, right? And XL is nothing but directly proportional to the frequency, change into the frequency. This is nothing but, let us say x-axis is nothing but the frequency axis. Okay, so this is nothing but representing XL, that is nothing but omega L, and this is representing XC minus JXC, right? Minus JXC is equals to 1 upon omega C, right? It is X omega L. Okay, and finally Z, this is nothing but my resistor, value of resistor. And then if at resonance, what is going to happen? The values of XL and XC are going to become same, and the impedance curve is going to decrease from infinity, and again it will increase towards infinity as XL is going to increase, because Z is equals to R under root of R square plus omega L minus X omega C, 1 upon omega C square, right? So remember that at initial condition 1 upon omega C square is infinite, So Z is also infinite. Yes, Z is also infinite in that case, right? So that's why this is nothing but the curve for Z impedance. Okay, so this is the curve for impedance. Are you getting it? So this is the curve for impedance, and it is going to come down from infinity because at zero or minimum levels of frequencies or minimum values of the frequencies, it will have maximum capacitance. Okay, and inductance is going to increase. So as we are going to increase the frequency, the value of inductor is, that is inductance, is going to increase and this value is going to decrease. So that's why this curve is going to come down, right? And at resonance these two values are same. At resonance these two values are same, so that's why it is having the value as Z will have value as R. And after resonance what is going to happen, this value is going to still increase, this value is going to still decrease, and because of that the resultant impedance is again going to increase. And if you are going to increase the frequency, again it will increase. Is that fine? I hope this curve we understood properly, right? This is nothing but the curve for inductance, capacitance, right? 1 upon omega c. This is the curve for XL, right? And this is the curve of resistor. Okay, fine. Now let us discuss the phase angle. Okay, so phase angle curve. So remember that resistance will not have any kind of phase angle relation. Okay, and let us say this is nothing but my resonant frequency. Okay, before resonance definitely the capacitor is predominant. Okay, so we can say that the predominant circuit or the circuit will have impedance as capacitive impedance. Okay, so capacitor angle is going to decrease from minus 90 degree. Okay, and at resonance the value of the value of phase angle of inductor and capacitor is going to become same, and therefore this is nothing but the zero phase angle. Okay, and after resonance what is going to happen, the circuit becomes inductive. Okay, because as the frequency increases the inductance is going to increase, right? Okay, so this is nothing but a phase angle curve. Okay, so this is, we can say that 90-degree phase angle. Okay, so this is inductive circuit, this is a capacitive circuit because capacitor is predominant. Okay, over here inductive, and this is at resonance, it is purely resistive circuit. Is that fine? So this is nothing but the phase angle curve. Okay, and last we are going to discuss voltage current curve, voltage current and impedance curve. Okay, so remember that what is the impedance curve? We have already discussed about impedance curve. Impedance curve is nothing but this kind of impedance curve, right? And what is the relation between impedance and current? V is equals to IR, no? Now instead of R, let me write IZ. Okay, impedance, Z is impedance. Okay, so therefore what is I? I is nothing but V divided by Z. Okay, if I want to have the relation between current and Z, it is nothing but inverse relation. Okay, so if the current, if the impedance is having characteristic or curve like this, then exactly opposite the current is going to have. Current is minimum if the impedance is maximum, and at resonance the current is going to become minimum, right? Isn't it? So remember that this is nothing but my current and impedance curve. So over here Z and I, and this is nothing but the frequency, and at this is nothing but my resonant frequency. Okay, so at resonance frequency, impedance, that is Z, is minimum and current is maximum, right? At resonance, as I told you in the very first or the beginning of this particular lecture, at resonance current is maximum, I is maximum, because Z is minimum, because Z is becoming purely resistive at resonance. Okay, so at resonance impedance is purely resistive, right? So that means this particular resistance value is there. Let us say it may be a 10 ohm, it may be a 100 ohm, like that, right? So it is having some finite value. Okay, fine. So over here we will stop and we'll continue in the next lecture. I hope you understood whatever the things that I wanted to discuss, and you have understood everything. Okay, fine. Thank you.